Hi, good morning. Today I'm going to cover in this office hour a few things. First, we're going to start with the project, and then I'll review some problems that are similar to the homework assignment or just give some hints on the homework assignment number 2. So before I start, I just wanted to know if any of you have any questions on the project. Or the other question that I have is that I wanted to know if everyone now has a partner for the project. So we make sure that we have teams of 2. So think about it as we go through this session, and then at the end we will make sure that everybody is teamed up. So let's get started. I will first talk about the project. So I'll share the screen here. And this is the project manual, which is being updated now. And Andrew is going to upload a new version this week. And the new version, the only difference is that it's going to be more linked to version 5.2a from COMSOL. So there's a change because in the manual we have version 4.2, and now the newer COMSOL is 5.2a. So this is going to be only in one chapter that we make the change. So the project at this point, we need to have preparation for progress report. And the progress report is due at the end of the 4th week. So we have a couple of weeks to go through that. So we'll just discuss what is required for the progress report at this point. First, forming the team is very important. I think most of you have team members right now. And hopefully by the end of this week, everybody's teamed up. Then you have to establish an account in CSNet. CES is School of Engineering and Applied Science. And once you establish the account, then you can access the remote desktop connection. And the computer name is remote.ces.ucla.edu. So once you connect, you have your username that you established with CSNet and the password. And you log on to the CES lab. And then the first part of the project that is needed, hopefully this week, is to do load analysis. So by the 4th week, when we submit the progress report, we would need to have selected the engine, selected the characteristics of the engine, maximum torque, maximum RPM, and that can give us an idea about the weight of the initial weight or size of the connecting rod. And then after this selection, we will do 2 or 3 tasks by the 4th week. First task is what are the loads on the connecting rod, and how to calculate all of the loads on the connecting rod as a function of time, as a function of RPM, time or RPM. And then second, once we determine the loads, is how do we translate these loads from a dynamic time-varying conditions to a static, equivalent static loading on the connecting rod, in which we move from an inertial frame to a frame attached to the connecting rod. So the connecting rod will have essentially static forces on it that allow us to do the analysis in COMSOL under static conditions without worrying about dynamics and vibrations and elastic waves and so on. So this is the first step. And then once we do that, then we have to use our knowledge from the course to select the material, and then we use our knowledge to draw shear force diagrams, bending moment diagrams, from which we're going to analyze the connecting rod initially as a beam. So when the connecting rod is a beam, it will have a load in the form of moments and axial, so the moments and axial, and it will be considered as a beam column. The column has axial forces, beam has transverse forces. Once we do this, then we are able to roughly get an idea about the size and the geometry as if it is a beam. Then we move on to the next step, which is two-dimensional analysis, finite element analysis, and that we will do in COMSOL. And then we will finalize the step and get some form of optimization. We can change some sizes, some fillet dimensions, and then prepare the progress report on the 4th week. All right, so what the task ahead of you this week is to do kinematics. And the kinematics is basically vectors. So if you look at what we have here is the connecting rod is this line represented by red line RP. And there is a vector. So if we take the center coordinates as a crank center, so the crankshaft is going from O to R, and the piston is connected to the end point of the connecting rod. So the piston is going up and down vertically on that line. So there's a cylinder around point B, pushing on the connecting rod sideways, and then from the top, on the top here, there's a pressure coming down. And the connecting rod now has to take the pressure force, which is coming down to point P, and some side forces, and the side force is coming from the cylinder, because if there's a little tilt on the cylinder, then there's going to be some side forces on point B. And it is driven by the crankshaft that is rotating counterclockwise, angle phi. So there's an angle phi here, and then the piston, when it moves up and down point B, there is an angle called gamma, and gamma is the angle of the connecting rod at point B, and there is a relationship between this angle gamma and the fundamental angle phi. So the most important angle is phi, that describes the motion of the crankshaft, and the time derivative phi dot is essentially the RPM, omega, or the radial velocity, omega. So omega is this is a constant value, omega. So phi dot is a constant in this analysis. And as we change phi, then gamma will change, and the relationship between phi and gamma is through the projection of R. If you take this line, you connect R projected normal to OP, then this length here is the same for the upper triangle as for the lower triangle, and that gives you a relationship gamma, sine gamma times R, like this length here is RP sine gamma or OR sine phi. So you get a relationship between the two. So the kinematics is describing the vector R and the vector G and the vector P. So the three vectors. R, G is is the vector from the center to the center of mass of the connecting rod. So G is the center of mass of the connecting rod. And it's all geometry. So if you look at this here from vectors, the vector R has two components, from O to R, has one component in the Y direction and one component in the X direction. So the X direction is negative in this case, and in the Y direction is positive. So you have minus R sine phi, and I with this little hat is a unit vector in the X direction, plus R cosine phi, and J with the hat is a unit vector in the J direction. So now we described R in terms of the angle phi. We can also describe P in terms of the angle phi, but then we see that there's an angle gamma as well. And it's all in the J direction because P moves up and down vertically only because it's constrained by the cylinder. And then G is the objective, because this is the center of mass of the connecting rod, is a linear combination of R and P. So from vectors, we see that G is R plus beta times P minus R, and beta is a ratio of the distance of the CG of the connecting rod to the end connected to the crankshaft, divided by the total length of the connecting rod. So beta will depend on your design, and your design will have to find this CG where it is in the connecting rod so that you can determine beta. So this week, you're going to obviously review these three equations. They're pretty obvious, but now the point is that you're gonna have to take the derivatives of these because we want to find accelerations, time derivatives. So you have to do hand calculations. I would like you to derive the equations. You take dr by dt and d2r by dt squared. So every time you take dr by dt, the only thing that is variable is phi. Little r is constant, little r is constant. So when you do the derivative, then you do the chain rule. So you have dr by dt, it's like dr by d phi by dt, and then you just go across to do this derivative twice. So you can r double prime, p double prime, g double prime, or double dot. And I wanted to show this assignment here by your hand. You can, if you have the time, you can type the results of your derivation, or if not, then you can just write it by hand and take a picture and attach it as an appendix to your progress report. So the objective in this case is to get gamma dot, gamma and double dot. That is an intermediate step. And then you use these to find R double dot and P double dot and G double dot, and prove these relationships. That will be important in the dynamics section. So after we do this task, then we need to know forces, because this is just geometry. Like the R and P and G is geometry, and we need to do forces. And the forces means mass times acceleration. Now the accelerations are R double dot, G double dot, P double dot, especially G double dot is the important one here. So how do we do the force analysis? The force analysis, we have a pressure that is driving the system, and that pressure is dependent on the particular combustion process and the energy in the combustion process. So for every engine, there is a pressure profile. When the spark plug just kind of starts, it ignites a certain amount of fuel, and there is an energy that is given for every mass of fuel. You get a certain amount of energy. And when this energy is released, then it shows into a P times V type work. So that gives you a P as a function of time. And in this case, we have a file called pressure.mat. It's a MATLAB file that has time on one side, and it has the pressure on another side, which shows a pressure profile that goes up and down. This particular pressure profile is relevant to a specific engine that we have, and it may or may not be the same as the engine that you chose. So at this point, you have two choices. One choice is that if you find a pressure profile for your engine, then you can digitize it and use it the same and replace that MATLAB list. It's like 2 columns. Or you can just directly use the pressure profile that is supplied in the manual. But if you use it, you just have to know what it means, and if you can figure out the relationship between that pressure, at least the peak, and the pressure that would be relevant to your the engine that you chose, because every engine has a different pressure. The higher the pressure, obviously, the stronger the connecting rod and the bigger that you'll have to do. So anyway, so you have the pressure as a function of the crank angle, phi, and the area of the piston is known. So this is also from the selection that you'll do. And then we have, our job is to determine forces as a function of time. So, or a function of phi. So everything, phi is a function of time, obviously, so we can do everything in terms of phi. So we have now capital phi is a notation for forces. So capital phi, C on P, this is cylinder on piston, which is kind of X component because it's sideways. And P on R is the piston pushing the connecting rod. And S on R is the shaft pushing the connecting rod. So the connecting rod, if you look at it, the piston is acting on the connecting rod in this direction, and the shaft is acting on the connecting rod in this direction. So the connecting rod, it has some concentrated forces on this end, P, from the piston, some concentrated forces on this end from the shaft. And then we'll find out that at the CG, there are body forces due to inertia of the connecting rod. So these forces are dynamic forces. When we do the conversion from real dynamics to equivalent statics, we will find that this means that we have body forces and moments at point G. So you have forces at P, including pressure, body forces at G from the dynamics, and then forces at R from the shaft, crankshaft. And so your job is to do momentum balance, mass times the acceleration. So if you look at this, mass of the piston. So this is a Newton's equation of motion for the piston. Mass of the piston times its acceleration is equal to the forces on it. So the forces on it is in the J direction and the I direction. The J direction are from the pressure, negative, and from the piston on the rod. And the I direction is from the cylinder hitting the piston sideways. This force is kind of difficult because it can, like if the cylinder kind of tilts a little bit, then it gets pushed back and forth, and we will ignore it because it can complicate the analysis. And right now we're just kind of doing a kind of first level analysis of that connecting rod. And then you have the mass of the connecting rod, like here, this equation, mass of the connecting rod times its acceleration, has the forces from the piston on the rod and the forces from the shaft on the rod. One from end, one from the other end. And then we have angular momentum balance. So this is linear momentum. Mass times acceleration equal forces. Angular momentum is the polar moment of the connecting rod times its angular acceleration in the k direction. K is out of plane, and this is equal to the moments that are applied on the rod, which is the cross product of phi from the piston on the rod times the arm length. So this is a moment is force times the arm length, but we do it in a cross product because it's a 3D. So it has to be done in vector cross product, and then from the shaft on the rod times its arm length. So you notice that this equation 2.7 is pretty much similar to equation 2.6, and both of them are for the connecting rod, one linear, one angular, while equation 2.5 is for the piston. So once you have these equations, they're pretty obvious. Then you take these equations and you want to show, again by hand, the forces now, that this is the final result. The forces in the x and the y direction. So we have two forces, piston on the rod and then shaft on the rod. Each one has a y component and it has an x component. And that you would show by hand. And these are the bases for us to do analysis for these forces on the connecting rod as a beam. So now we have determined the forces. We need to do a little bit extra work so that we don't want to study the connecting rod in its inertial frame. We want to move it from a non-inertial frame to a reference frame. And that is by finding the acceleration of the connecting rod. So we have the velocity in 2.8, and the acceleration is by taking the time derivative of x dot one more time in 2.9, and then you put it finally in, you move it from being in vectors, this is all vectors, to components. So x double dot has a component in the x direction, the y direction, and the z direction, and all zero in the z direction. But you have x and y components. And this equation 2.10 gives us the acceleration components of the connecting rod in its CG. So this is like rigid body. Now the whole connecting rod is assumed to be focused in its CG and moving with this x dot double dot in three-dimensional space, but here actually in two-dimensional space because it doesn't move out of plane. And if we multiply the mass times this acceleration, it gives us equivalent body forces. So it's like an equivalent body force that we can derive. So from equation 210, multiplying by the mass of the connecting rod gives us the body force in the axial direction and the body force in the tangential direction. And those now are to be used in constructing the total force distribution on the connecting rod. So at this point, you know, these are, once you do that, you can do it by hand, but then you have a MATLAB script that you could use, and the results of the MATLAB script would be these forces, axial and transverse, as a function of the crankshaft angle in radian. And you can see, you know, you have to use this combustion data, and I would say that you can use it directly from the MATLAB code that you have, or if you have something better, you can do it. It doesn't matter at this point, but you have enough information now to construct this picture of the connecting rod. This picture has one end has force from the piston on the rod. And the force has an axial component, which is in X direction, and a transverse component. T is transverse, A is axial. So these are two components coming from the piston. On the other end, which is the shaft exerts an axial component and also a transverse component. And now at the CG of the rod, we have now found the mass times acceleration in the axial direction and the mass times acceleration in the transverse direction. These are to be subtracted so that we can transfer to the non-inertial frame, and these are the body forces on the connecting rod. In addition to this body force, we have also a concentrated moment due to the rotation of the connecting rod, and this is similar to saying mass times acceleration. We have here J times the angular acceleration. So M is like J, G double dot is like gamma double dot. And these three here are to be included in beam analysis. So in beam analysis, we have beam column, we have two components here, three here, and two here, and then we are to construct the axial load diagram, like here, and bending moment diagram, and then the variation of the x at certain angle. Like if you just, these are variations as a function of angle, so if you change the angle, all of these forces will change, and you have them here. The code can give you these numbers, but if you just take one particular angle, you can make the distribution of the axial or axial forces, transverse forces, and bending moment diagram like we have in class. And once we determine that, then we use the beam theory. The stress is axial stress, P over A, and bending stress, My over I. And that's kind of what we need. You have a numerical implementation here. So you're now looking at it as a rectangle for the beginning. You can do it rectangle, or you can do it an I-beam at this point. So you can do an I-beam, and the I-beam will be less weight to give you the same kinds of stress levels as allowable by the code, because you have the information on the material and the yield strength, and you can determine the size at this point. Finally, which is Andrew is working on, is COMSOL 5.2. This section is going to be replaced soon, this next couple of days. And this section goes through selecting the space dimension, selecting the solid mechanics analysis, the physics, selecting the study type is stationary, it's not time dependent. Once you select this, then you have to do solid modeling first by going to the geometry, and then it shows you how you make the connecting rod as a bunch of circles connected with a rectangle, and doing a Boolean operation to connect them all together. So this is all here. You have a circle here, rectangle, and then you just add them together like a Boolean. Then it just connects. The console knows how to add them. And then you can also subtract another circle in the middle, subtracts here. So essentially, after these Boolean operations of two big circles, one rectangle, and two smaller circles by subtraction, you can get this shape. And then you can add fillets at these locations. And the fillets will look like this. Otherwise, you'll have stress concentrations here. And that's in COMSOL. SOLIDWORKS, if you're familiar with SOLIDWORKS, you can, or you just follow some of the instructions, you can do the same thing much easier. You can get a 3D initial figure of the connecting rod. And this is, by the way, a simplified picture of the connecting rod. You know, as we move on, we're going to build it to be much more realistic. But this is enough now to do finite element analysis. But before we do that, we have to create contact pairs, because the shaft is inside here and the piston is inside here. And then we have to make sure that they can't contact at these surfaces, because this is where the forces are going to be transmitted. And that's kind of an important step in the analysis, without which we wouldn't get the correct stresses. And finally, you get the two-dimensional elastic analysis that will give you some stress distributions, going from the pressure data to finally getting stresses in the connecting rod. So here's the issue of the mesh, and then you're setting up the solver and getting stress distributions. So all in all, in 2 weeks, we expect that you and your team member would get something like that, which shows you the distribution of the stresses. This is shaft connected, the piston connected here. You can see there's a gap here because it's actually depends on the angle. So you have like contact at this surface, contact at this surface, and then you get a deflected shape from the connecting rod and the stresses. So I think this is what I wanted to review for the project so far. That gives you enough information. Andrew will be available for any additional questions on the software. Also, what I wanted to do is encourage all of you to use the forum. And in the forum, you can send your inquiry, and then other people or students in the class, or myself or Andrew, will monitor this and then respond with resolution of basically software type questions or issues related to the project. Okay, any questions on the connecting rod? Everybody's okay? Can I move on? Just get a sense that everybody's is hearing me. Anybody's hearing?
I can hear you.
Can I please just let me know if you hear me?
I can hear you.
Yeah, I can hear you.
Yeah.
Nick, do you hear me?
Yep, can hear you.
Hello?
Yes, I can hear you.
Hello, anybody here?
Yeah, I can hear you.
Yeah,
Yes, I can hear you.
Yeah.
I can hear you as well. I'm also using the group chat too.
Hello?
Hi, can you hear us?
Hello?
Hi.
Oh, okay. So are we back now? Can you hear me?
Yeah.
Yeah.
Oh, okay.
Yes.
All right, great. So I'll just continue then, because I just stopped for a minute because I didn't know that everybody's there. Does everybody have a question? Anybody has a question? All right, so moving on. Then what I'd like to do is continue to work a little bit on the homework. So now we discussed the project. We have some time now to discuss problems related to the homework assignment. So in here, I'm going to discuss problems related to the homework assignment, and I'm just sharing the screen with you to give some hints. So let me just kind of get this out of the way. Yeah. So we have a problem. The homework assignment is designed to review basic beam theory and two-dimensional stresses using Mohr Circle, and combinations of understanding load distributions to the point that we can compute stresses on the beam, including shear stress. And that is very mirroring exactly what I discussed in the connecting rod project. So this problem here, we have a distributed load, and the distributed load, we have two simple supports. So at these supports, we have reactions, and the distributed load is W in pound-foot per inch. And these reactions, obviously, they will be exactly equal to W times the entire length of the beam. And then half of it will be here, half will be here. So it's WL/2 at each one. So now if we cut the beam at some point here, we can do a force balance and a moment balance. And the force balance will give us the V, and the moment balance will give us the M. So the stresses on this beam are due to the moment, and the moment will vary from 0 at this end to some kind of maximum at the reaction point, and then it will go down and continue on to here. So there's a moment distribution along the beam. To find the moment distribution, if we just cut at the generic point as X, we can show from the moment balance that the moment is dependent on two things: dependent on X, which is very natural, but also dependent on the distance A of the supports from the free ends of the beam. So it has two parameters. One is X, and one is if you just kind of change the support. And that is not so difficult to find that this equation by just taking this picture, and then you can find the equation. And A is the substitute given the value of A, and then substitute here, find the magnitude of the severest bending moment. And the severest bending moment will be the highest, and that depends on where X is. So you can maximize this function, finding the maximum value dependent on X. So if you dm by dx, you set it to 0, then you get the maximum value. B is different. So in B is saying that there is a moment at these reaction points, and then there is also a maximum moment that you can obtain from maximizing this equation. And you find that there's a difference between the moment at the supports and the moment at the maximum. So it depends on what A is. So for the designer to design the lightest beam, it's the best way is to kind of even out these 2 points. and we wanted to find the optimal setback A that will result in the lightest beam, which means that now you're going to have to find the dm by dA, like if you have the optimal distance is that when the m at the reaction point, m at the reaction is equal to m at the center of the beam, because the center of the beam, you have the moment is going to go the maximum at the center of the beam. So that's kind of the key idea of that problem. Next problem is a variety of Mohr circle, and you get in Mohr circle, the idea is that you get sigma x, sigma y, tau xy, and you find a bunch of things. And a bunch of things would be the maximum shear, you find the principal stresses, and you can make a transformation from one angle to another. And for this, I'm going to just show you that the review of how this works. It gets here. Yeah. So in this review, for Mohr circle, just wanted to have the Mohr circle only right here. We get three numbers, sigma x, sigma y, and tau xy. So from the first two numbers, x and y, we find the center of the circle. And the coordinates, as you know, that we have the vertical coordinate is for the shear, and the horizontal coordinate is for the axial or normal stress, either sigma x or sigma y. So in here, the center is located on the horizontal, and that's why the vertical is 0, the coordinate, and the horizontal is the average value of sigma x and sigma y. So we can determine the center of the circle, and the center of the circle is C, and this is midway between sigma x and sigma y. This is sigma x here, and this is sigma y. And then the other important part of the Mohr circle, once you determine the circle, we have to determine the radius, and the radius is the square root of tau squared plus now sigma x minus sigma y square over 2 squared. So this is the difference here, and that gives us the radius. So from the C and R, we can draw the circle. But we note here that in point A, the coordinates of point A is sigma x and tau xy, but this tau is counterclockwise. So what I wanted to show you here is the situation in regards to the convention. So the convention that we have is that you can see now is that on this square here, which is an element, the positive tau xy is up here, but if you look at it, it is going counterclockwise here. And it is associated with sigma x. So whatever sigma x is, tau is counterclockwise. And whatever sigma y is, then it's associated with it is tau. This is clockwise. So the coordinates are this sigma x and tau counterclockwise, and sigma y and tau clockwise. Because when we plot the Mohr circle, we have in the vertical, it's always the vertical here is tau clockwise. So what if you get positive up is clockwise, negative down is counterclockwise. So when you have sigma x, you attach to it whatever stress, shear stress is on it. If it happens to be counterclockwise, then it has to be down. If this happens to be clockwise, then it will have to be up, because the positives is assumed to be clockwise, and the negative is assumed to be counterclockwise. So these are the principles that we use, and here's an example. So if you look in here, I have sigma x is 80, and tau xy is 50, and it says clockwise. So 50 clockwise going down. And of course, it has to be balanced by 50 counterclockwise associated with the y component. Here, the y component, sigma y, is equal to 0. So immediately from here, I have the c, the center, is the 80 plus 0 over 2. And the radius, I can find it from the difference between sigma x and sigma y over 2 squared plus tau xy squared. So I found the c and the r. And now what is left is to find the coordinates of point A, which is this combination, and point B, which is this combination. So point A, I have sigma x is 80, and tau is clockwise, which means that this is going to be in the positive quarter. And that's what you have here. So this is sigma x is 80, and tau clockwise is 50. So it goes up here. And on the other side, sigma y is 0. So this is 0, the vertical axis. And then we have tau counterclockwise is 50. So that will be the condition A to B is the current condition that we have. And the angle that we get is 51.3 degrees. And we get the maximum shear is 64, which is the radius of the circle. And the principal stresses sigma 1 and sigma 2 are the extremes in here, according to tau 1, and we get sigma 1 and sigma 2 from this example. So this example, this is similar to what we have in the homework assignment, and that gives us solution that we required here. So moving down, you're going to solve this. Moving down, we have another type of problem is these types of problems. You have beams. Now, like the connecting rod will be like an I-beam, could be, or it could be like an H kind of beam. So these are all problems of area. Problems of area, meaning that we want to find the CG, center of gravity, or center of the area, and we want to find the second moment of area. So if we take, for example, this H shape, then what we do is we section it. We have a rectangle on the right and an identical rectangle on the left. So we know that the center is going to be, the center of the area is going to be right along the vertical direction here. And then we will take a rectangle in the middle. So we have a rectangle A and an A and a rectangle B. And each one has its own area. And we find area B, and the total area. And we find the Y bar, which is the CG in the Y direction by knowing the Y bar for A. So we have 2 times that, 2 times the area times Y bar, plus the Y bar for the section B, and divided by the total area. So that's kind of where we find the center. Once we found the center, the location of the center, then we need to find the second moment of area about that center. And in this case, we use a few simplifying ideas. One of them is that we always try to divide up the section into rectangles, and we use the idea that I is equal bh cubed over 12 for each rectangle. And then the second idea is that if we get the second moment of area about the axis passing through the centroid of an area, then we can always move it from that area to wherever we want to move with the parallel axis theorem. So we just add the area times the distance squared. And that's here the idea. We have I for area A, BH cubed over 12, I for area B, BH cubed over 12 for it. And then when we do the total I, then we have to take 2 times these, and then it will be the I of each one plus the area times the distance square for each one. And then we add it, so we add all of these 3 together. So this is an idea here. There's a bunch of ideas. When you have like an I-beam, you can take the I-beam simply as the difference between a rectangle on the outside, and you subtract the second moment of area of 2 rectangles that are carved on the outside. So subtraction is okay. You can do it by one big rectangle and then subtract smaller ones. So this can work with subtractions. This here can work with a big one, and then you subtract the smaller one here and another one here. So subtraction, you can do 3 moments of area, and then you subtract 2 out of the big one to reconstruct it, and so on. So these are kinds of problems on the properties of area. Now there's another problem here on distribution of shear forces and moments, and that would be similar to the connecting rod idea, that we have a uniform distribution, concentrated force, and the beam has this cross-section area as T, inverted T, and we want to find the distribution of shear and bending moment. So here the shear would be down minus 1800. You get a reaction here and a reaction here, and you wherever you have a reaction, then it will be concentrated force. So you go down, this is down, will be minus 1800 because it's going down. The reaction is up, so you go up 5100, and then a distributed force, you integrate that, you get a straight line down to the reaction here. And the moment is the integration of the shear force. So every rectangle, you integrate it to get the coordinate, which is the moment at the end of this period here. So this is linear, straight line. This is a constant, then you get a straight line, and then you have a straight line here, you get a parabola that you have. So this is basically hints on this problem. One other issue in this kind of problem is what is the shear? What is the worst? You know, these problems are designed for a particular reason. So the reason here is that we want to know what is the worst location. Where do we have to worry about? The maximum shear or the maximum bending moment? If we have a maximum bending moment, then we would have to find the corresponding stress by taking the maximum bending moment. So here, maximum bending moment would be 25,350, and the maximum shear would be 5,100. So you have a shear stress at this point, which is pretty bad, and you have an axial stress at this point, which is also bad. So the idea here is to find the shear stress, which is VQ over IB that we have in the lectures, and that will be the worst point. And the maximum moment here, M times C over I. See, and then we can also, if we have shear force giving us VQ over IB here is a transverse shear, and we have a moment minus 18,000 here. They're giving us axial. So we can also combine them using Mohr Circle that I talked about, so that we can find the maximum principal stresses and determine if they exceed any allowable. So this is the kind of idea behind the assignment here. So finally now, before we close, I just wanted to discuss what is coming up this week. And this is stresses. So there's now we learned distribution of forces, distribution of moments, and how we obtain them. We're going to do more of that to find deflections in the next week or so. But before we go to deflections, we have to review all of the formulas for stresses in mechanical components. And the stresses are going to be basically related to cylinders. So we'll review the stresses on cylinders. We have internal pressure. How do we find the tangential stress? And the hoop stress is a tangential and the axial stress. And then we will also review rotating rings when we have a ring that is going at a speed omega, and what is the corresponding tangential and radial stress. This is a function of the position R. And one important system is press fits. When we have shafts and we fit one shaft that is hollow inside another shaft, but the fitting is not perfect. So at the interface, we have an interference, delta. So this interference creates an interfacial pressure that given by this equation, and we can find the stresses. And we will discuss also curved beams and find the stresses in curved beam systems and contact stresses. So this is kind of before, we started a little bit of lectures this week on stresses in different components. But by maybe middle of next week, like by Tuesday, Wednesday, we should have now all knowledge, all of the equations that we will use to calculate stresses in pressure vessels, thin tubes, rotating rings, press fits, contact stresses, using Mohr Circle on all of these, and finding torsion, the stress due to torsion, the stress due to bending. All of that would be the elements that we will use in the rest of the class. So I think I'm going to stop here, and I'll pick up on the stress idea next time and discuss any relevant problems related to the stresses. So I'm done. I think I would like to see if anybody has questions. Okay, so I think we're done, and we'll see you guys next week. Have a good weekend.
Thank you.
Thanks, you too.